of astronomy. I've known him for a long time. I remember the last time I was in Australia. We drove the 8 hours up to Coonabarabran. Coonabarabran. I knew I'd mess that up. And with Cedric Lacey, and I think Joss and Cedric figured out the entire world's energy problem. And I was deeply impressed by him and by the AAO. But especially by the fact that even though he was driving, we didn't hit a kangaroo once. So,
I have since, but
it's almost inevitable in Australia. Joss is the ARC laureate professor at the University of Sydney after a career that's taken him all the way from England through the United States in several positions, and finally to Australia. He is the director of the SIFA Astronomy Group. That's the Sydney Institute for Astronomy. He spent most of his career working on the Milky Way local group and instrumentation, and he is one of the key developers of the photonic lantern, which is one of these beautifully named, intriguing instrumentation approaches, which has many applications to astronomy, as well as many other applications. He's the project scientist of the SAIL labs. That is the Sydney Astronomical Instrumentation Lab, I believe. He builds astronomical and space instrumentation, including the SAMI instrument, which I believe is an integral field spectrograph, and the next generation SAMI called Hector. And he has been involved in the launch of a CubeSat to the space station in 2018. He was the Miller Professor at Berkeley in 2018. And he's the project scientist of the Galactic Archaeology survey, which I believe he'll be talking about results from that as well. And he notes that for those of you that haven't kept up with Australian astronomical astropolitics, the AAO is now split across 3 universities. One is part of the University of Sydney, where he is the professor working in the SAIL labs, and the other 2 components are at the ANU with the leadership by our own Anna Moore and Macquarie University in Sydney. So with that, I will introduce Joss's talk, which is intriguingly titled Galactic Seismology, the Evolution of the Phase Spiral After the Sagittarius Impact. Take it away, Joss.
Thank you, Chris. That's very kind of you to introduce me. Do you see my first slide where it says the title?
Yes.
Good, so my screen's sharing correctly. Okay, great. So galactic seismology, that language, in fact, I think of that as a subset as galactic archaeology, really came from Lawrence Woodrow in Canada, as I'll mention as we go along. I want to give special thanks to the Gaia team, as you'll see also the Gaia team later, and Torsten Tepe-Garcia, who's this wonderful colleague of mine who does much of the simulation work with me. So you're all familiar with this incredible rich era of galactic archaeology. I saw Judy's name on this list. She will be well aware of this field in general. It's not just Gaia, it's NASA Kepler, NASA TESS. We've got immense information now on millions of stars, billions of stars if you include photometry. We have astrometry, and we have precision measurements on temperature, better ages than we had before. And we also have 6-dimensional phase space information on the sort of a sphere of about 100 parsecs or so, which I'll mention as the theme of my talk. So this is an image reconstructed in color from the Gaia survey of something like 100 million sources across the sky. So one of the wonderful things nowadays is that we have data from across the entire spectrum. We've even got good photometric distances in the mid-infrared, and you can look out across the galaxy. Those of you that don't work in this field, look off in all directions and do some kind of thermographic reconstruction of what that looks like from mid-infrared colors. And you get this. This is a rather nice reconstruction of what you would see if you were external to the galaxy. This is by Ness and Lang. It's been done different times, in the past. You can even see that the inner bulge is somewhat flattened. You can just about pick up a thick disk of stars around the thin disk. And there are also various things up in the halo. So this is a really beautiful image because it shows just how thin the inner disk is. And I want to make that point that well, I'm going to show you all sorts of evidence now of disequilibrium in the galaxy, giant waves and things that have been known about for a long time, but in a rather coherent fashion now. It's more of a coherent picture. And there are models, there are people speaking about that the bar might be doing this. The bar is buckling around and doing all sorts of driving waves into the disk. But if you look at my review with Otto and Gerhardt in 2016, you'll see that the inner bar, which is sort of fat in the middle and gets very flat further out, are lines with the very thin and very clean inner disk to within a couple of arc minutes in physical angle in terms of the actual three-dimensional space. So it's very hard, I think, to think about anything in the outer disk as being driven by the inner disk. Some interesting dynamics of the inner disk driving these waves moving outwards, although this does become a part of the story in the future, I'm sure. So anyway, it's a rather nice reconstruction, but we've gone way beyond photometric distances and three-dimensional reconstructions. We now have dynamics. So the one problem in galactic archaeology is we want to understand, using the ages of stars, we see stars back to redshifts of 5, 10, 15, depending on the model. So we see very ancient stars. In fact, half the stars in our galaxy were formed before a redshift of 1. So you've got, that's at the point of Freeman and Bland-Hawthorn 2002. We were trying to make the point that you can, rather than using having far-field cosmology looking at redshift, you can use the slicing ages of stars, especially if ages get better, and basically look at the reconstruction of the galaxy, and we call that near-field cosmology. So the trouble with the whole of galactic archaeology is you have to define the figure that you're working with, the space, the framework that you're working with. And people like Biniam Tremaine, in the book, makes the point that this is probably not an equilibrium figure. And that what you're seeing today are strong departures from equilibrium. And the ultimate goal, as you probably are well aware, is that you want to form a potential density pairing, basically reconstruct from distribution function of stars the actual overall density field and potential that the stars move in. And you're doing this for multiple components, multiple populations. It's very hard to do. So the way that you do that is you work with motions in 3 dimensions. That's Vz, V phi. Vz is vertical to the plane, Vr is the radial motion, V phi is a tangential motion. Or you express it in terms of actions. This is work that Biniam in particular has been pioneering for a long time. And these are constants of motion, supposedly adiabatic invariance. But the point that Freeman and I make in the annual reviews 2002 is that they're not very good, actions are not particularly good invariance. They may be good for some number of rotations, number of orbits, but not over the lifetime of the entire galaxy. So for us, stars, the chemistry of stars in high dimensional space was a much better surrogate for a tag. So we call that chemical tagging. We basically want to try to reconstruct. We feel that stars will retain their chemical properties in high dimensional space from almost their entire existence. So I'll get into this point later on about what's valuable information in terms of chemistry and what's valuable information in terms of dynamics. So the point to make about this is that Gaia has now given us a sample of 7 million stars with very impressive 6-dimensional phase space information for a region of about 100 to 150 parsecs around the solar neighborhood. In the beginning of 2022, there will be 35 million stars over a somewhat larger volume. So you can begin to see that we're going to get a lot of information about the flow of stars in our neighborhood and over a larger sphere. So storm clouds on the horizon. So we've worked for up until relatively recently in terms of an equilibrium figure, and much of our thinking is done in terms of reconstructing something which is stable or in equilibrium. But there were always people saying, in fact, the evidence is that this probably isn't true, going way back to the art of warp, of course, back in the 60s and 70s. But more recently, there's the Hercules stream that was identified in UVW space. That's the local velocity space around the solar motion. Then there were various ring-like structures. Heidi Newberg has been very instrumental in making this clear about local departures from equilibrium and various structures with imaginative names. So a thermographic slice with the Sloan survey by Urich, for example, out to 8 kiloparsecs, you identify a halo, you identify a disk. But when you subtract a smooth halo and disk model, you have these sorts of plumes in the local stellar density. And this is a departure, obviously, from exponential declining disk. Is it sort of a flaring disk? Is it an outer warp, or is it an entirely new structure? And very often these turn out to be new structures rather than flaring or warps. Something else that's been identified by various surveys, SDSS, RAVE, and LAMOST, all made this point, that if you subtract some smooth kinematic model of the Milky Way in the local disk, this is now by LAMOST team, Carlin et al., plus or minus 2 kiloparsecs in the local neighborhood, plus or minus a few kiloparsecs in the other direction. You see the residual, you don't see a smooth velocity field. What you see is a sort of wave-like patterns in the kinematics. Same with north-south star counts. If you subtract the northern counts from the southern counts, you find the residual has a wave-like pattern. You see that you have an excess of counts, then a depletion of counts, and so forth. So there are a lot of surveys, photometric and kinematic, showing that there were really interesting departures from a smooth exponential disk expressed in density and kinematics. So simulations have shown for a long time how these structures can occur. Papers by Kentonidis and Young as examples, trying to produce the K-band light of a star of a galaxy disk face on that's been perturbed by a passing perturber, like a dwarf galaxy, and same thing in H1. And these produce nice external ring-like structures. And these are the sorts of structures which are now known to be occurring in our own galaxy. Others went a bit further and talked in terms of corrugations, that you don't just get projected structures. You also get basically structures which go up and down in kinematics and in position. The relative position, relative density, all these things show signs of a wave-like pattern through the galaxy. But what's not clear at all is how all this goes together. And in fact, what are these various wave-like patterns doing? And this is something I want to address in the new work and try to explain what Gaia is seeing. So this is the field that I've been referring to as galactic seismology. And this is basically accepting, this is not weather. I don't think all these perturbations is weather. I gave a Cavalry talk on this last year, which you can find online at UC Santa Barbara. David Gross asked me to address the question, is all the stuff that you guys are doing, is it basically weather? I don't think it is. I think it's looking at the natural responses and modes of the system. And until we don't understand the system, we could hardly call it weather-like patterns. It's because we have a lot of work to do to understand what all these effects are. But the language of galactic seismology really comes from Larry Widrow. He had a paper in 2012, a rather nice recent paper by Checkers and Widrow, where he looked at perturbations of a disk, sort of like setting a disk ringing. It would have a differential rotation, it would have an exponential density profile, and you see these rather interesting cylindrical patterns, and you sort of do Fourier-Hankel type transformations or whatever you like, look at these modes, and try and figure out whether you can interpret what you see in terms of perturbations based on the mode strengths. This kind of work, by the way, using Fourier transform techniques goes way back. There are people going back to even before 2000. In fact, the entire field, you can probably argue, can be traced back to Toomey and Toomey in the 70s. Anyway, what about the new era? Well, the new era is all about Gaia, and what Gaia revealed was quite astonishing. So first of all, if you plot the V-phi motions, remember now that you've got 7 million stars, and you've got 6 dimensions of phase space. So you're now able to compute the tangential velocity and against radius, and you know as well as I do that if that was gas or a hot, young population of stars, you'd see, this is 4, not 0, so 0 is out here somewhere. So you'd see a rising rotation curve, which would then go flat at about 245 kilometers per second all the way out in radius. That's not what you see in stars, because of course, almost all stars are precessing. They're trying to solve the Kepler potential and the spheroidal logarithmic potential at the same time. So that basically means that all stars are precessing by definition. Some are highly radial, some are somewhat circularized, and basically you see stars filling out this entire space. Because I'm not showing you VR and VZ yet. And by the way, the fact that you have a pileup of stars in density at 8 kiloparsecs is because this has not been corrected for the selection effect. This is basically overwhelmed by stars local to our neighborhood. But what was not expected were these ridgelines. They were suggested by some other surveys, but not seen in this clarity. And these ridgelines go a long, long way. You can trace them. You can see these slants, different slants through the velocity field. And you can see a lovely edge here that goes a long way in distance. Now, this has raised questions. Are these constant angular momentum? Are these constant energy surfaces? Are these turnaround points? Are there resonances due to bars? So it raises all sorts of issues, which I won't address today. Now, if you plot that same data, bringing in VR, the radial component of motion, now you see something which is highly complicated and clumped. So to be fair to Danon in 1998, he saw evidence of this in the Hipparcos survey and identified the so-called Hercules stream, these things down here, which are thought to be due to trapping by the power resonance in the disk. But then you see all these other clumps in the VR V5 plane. You can think of this as UVW if you like, W being vertical for the disk, out of the plane. And these various clumps that you see, small round clumps, like maybe this one, maybe in here somewhere, some of these would be open clusters, but the vast majority of it is not. It seems to be coherent moving streams or projections of some kind of resonance trapping. So these arch-like features, there's a lot of very nice papers now. I point you to Alice Quillen in particular. I think her paper is very nice, where she talks about sort of a holistic view of all these structures. Jane Finney, of course. Shoria Khanna talks about these bridge structures. He was my PhD at the University of Sydney, now working with Amina Helmi and Groningen. So there's a lot of work going on about what all these structures mean, and it really is quite revealing because you do this as a function of population and stellar age, stellar abundance, and so forth, and you do it as a slice in and out of the plane as well. So there's a lot of work revealing new insights. But my talk today is on something quite different. It's on the so-called phase spiral, or phase-phase spiral. This was unexpected. Nobody foresaw this whatsoever. So now we've got Z, which is distance out of the plane, and this is VZ, velocity out of the plane, plus or minus 60, plus or minus 1 kiloparsec. So it's a large scale effect in the local volume. So for example, if you had a simple harmonic oscillator, if you have a star that was going up and down, up or down with an equal amplitude, as you well remember from your dynamics days, probably in your school days, this would be a circle in this plane. You go from maximum Z to maximum VZ to maximum Z, maximum VZ, as the oscillator was converting potential to kinetic energy and back again. So, so that would be a circle. But notice now, you've got millions of stars. You don't see circles anywhere. What you see is a spiral all the way in to the center. And you can play with this in all sorts of ways. And there's all sorts of other interesting things that are revealed if you move around the local volume, go a little bit further in radius, or go to angular momentum and other spaces. It's been color-coded in terms of the tangential velocity. And it's very clear in this space. It's not so clear in other spaces, but it's clear if you color code, take the average or median value of the velocity locally in each pixel. That might be thousands of stars in each pixel, producing a range of values, and take the mean or median value. You get this beautiful V5 spiral. So where that comes from is not even appreciated fully by the community that work on this stuff. It's really quite subtle, which I'll get to now. But basically, the one way to think about this is this is not one star settling. If you watch one star, a damped oscillator, then that would track some kind of spiral and settle. You're seeing a sort of a coherent behavior over millions of stars doing this locally. So one way of thinking about that might be, say, sand grains bouncing on a drum skin. Then you bash the drum skin. As the drum skin comes up, it imposes some kind of order on some of the turnaround orbits, and then the drum skin stops vibrating, and the sand grains want to settle. So it's some kind of coherent effect due to an impulse of force applied to the local disk. All right, so this is the discovery paper by Teresa Antoja and colleagues. Now in surface density, this is the same spiral, but notice it's very hard to see. It's nothing like as clear as it was in the V5 encoding over here. VR, that's the radial component of motion. If you color code in VR, it's not quite as clear as in V5, but it's still somewhat clearer than you see in projected surface density. So the question is why? Why is this spiral so clear in V5 and less clear in other parameters? It's also, as my Shoria Khanna, my student's paper shows, it's also particularly clear in angular momentum, which we'll get to. So the answer was supplied by Binney and Schoenrich in 2018, but I found their answer quite difficult to appreciate. So in my new paper with Tepa Garcia, we've tried to give a simpler view of the phase spiral phenomenon. But they gave the correct, as far as we're concerned, they gave the correct interpretation. All right, so think of the local disk as being a cloud of stars, and all the stars are going up and down at different amplitudes. In action space, this would be an increasing amplitude, so increasing JZ square root of is the radius of these ellipses. So basically, any star going up and down is going in a circle around this center, like this, in the clockwise direction. And that's given by the angular frequency. So if you are close to the disk, you might have a very rapid angular frequency. If you're further away from the disk, your angular frequency might be somewhat slower. And it's given, of course, by the local surface density. So that's the first point to realize. Now, the next point to realize is if you perturb the local population, you offset that because you've punched through the disk with some kind of perturber. And then what happens is the stars are locally and instantaneously offset. And then at every point, the stars have different properties. You're looking at stars with different properties within the disk, with different orbits. But the ones with the higher omega z are the ones that move off ahead of the ones with the lower omega z. And this basically, this cloud of stars gets sorted based on omega z. So where does that sorting come in? Well, where it comes in is to look at the disk itself. So here we are in the local volume. If you've got stars reaching the local volume from the inner disk, they have the higher surface density regions where they've come from. They have the higher omega z. The outer disk, of course, is the reverse, much lower surface density, lower omega z. But in fact, if the stars reach you from the inner disk, they must have reached you from their apoapsis. If the stars have reached you from the outer disk, you're seeing them at their periapsis. So basically what that means is, because this is a flat rotation curve through the galaxy, roughly speaking, then you're seeing stars with somewhat higher V phi in this volume, and they have lower omega z, and you have lower V phi, and they have somewhat higher omega z. And it's this process which the simulations reveal to be true, which is doing the sorting for you, which is why, so basically what this diagram is showing you are stars of a particular V phi that are moving a particular omega z, and they move ahead of stars with lower or higher V phi. So there are all sorts of subtleties about these diagrams. My paper in 2019 took about other effects of the velocity ellipsoid, sort of a low order quadrupole effect, which you can also see, which wasn't picked up on by the Gaia team. But anyway, that's the main effect, which is the sorting effect from the stars in the local disk. Let me just mention briefly the Gaia survey. We've had a big release last Friday, DR3 we call it, 600,000 stars. This gives you 30 element abundances. It gives you better velocity precision than Gaia does in the radial direction. And the survey, I would say quite wonderfully, targets main sequence turn of stars because these are the ones that will always have the best ages, as we confirmed with Kepler, K2, and TESS surveys. The K2 gap survey has been led by the University of Sydney, in particular Sanjeev Sharma. So we've had we have a very large astrophysics team through Tim Bedding that does this for a living, and they've been able to give us very good ages for all of the stars in our survey, doing 10 to 20% rather than 30 to 35% accuracy. So the GLASS survey now has been going for a number of years. It uses the same 2DF positioner that was used for the Galaxy Redshift survey, 2DF Galaxy Redshift survey 20 years ago that I was a member of. There were 20 of us working on this. It was led by Richard Ellis, you might remember John Peacock, Sean Cole, and so forth. Richard, of course, a Caltech colleague who emailed me this morning, wishes you all well. So anyway, so Richard was a very prominent member of the survey. I was lucky to be part of the team. And when the 2DF survey ended, we then went on to do the use it for galactic archaeology with high resolution spectrographs, 4 very large high resolution spectrographs, different parts of the windows of the spectrum. But we're not living in isolation. We also work closely with photometric surveys, radio velocity surveys at low resolution. We work with seismic surveys. And of course, we work with these new astrometric surveys. So this is really is a golden era for galactic archaeology. Here's a snapshot that was made for me by one of the postdocs for various members of the team. You might know Michael Hayden and Sarah Martell from the Apogee survey. There's Sanjeev Sharma, who's so critical to our work these days. Young graduate student Ken Freeman, you'll recognize. Gary DaCosta, I'm sure. Melissa Ness. So anyway, there's lots of wonderful individuals in the Gaia team. And as I say, our big release has just been made open to all of you last Friday. So here's a demonstration of our radial velocities, because we use Gaia phase space, proper motion information, but we don't use the radial velocity information. We supply that for ourselves for the stars that overlap. So here's the Gaia velocity precision and radial velocity, and we combine that with the Gaia proper motion information. The Gaia radial velocities tail off in the magnitude range of our interest, which is really good because when you combine them, you can start to see things like open clusters and globular clusters and very thin cold streams in the local volume. So here's the point about the tagging. For us, the reason we went down the track of doing this high dimensional chemistry is because we don't believe that the actions are particularly good adiabatic invariance. And they're not seen to be actually in cosmological simulations of galaxies. For example, stars migrate, and you sure as heck don't conserve your actions when you're migrating between different positions of the galactic disk. The angular momentum exchange as stars start moving around. So for our stellar age, location, and motion, these are not invariant, of course. So for us, the chemistry was particularly valuable tag for us to learn something about where stars have come from. One thing to be aware of, these days we talk about alpha-rich and alpha-poor disk rather than thick and thin disk. You've got to be careful about that language, because as the apogee and Bland-Hawthorn surveys have shown, the disk is thickened over the conventional thick disk disappears by the sun's location, and then the outer disk essentially becomes thick with the alpha-poor disk. So basically it's a chemical distinction between these two components, and that chemical distinction depends where you are in radius. These, of course, was pointed out years ago by Gainsby and Sophia Feltzing. So I won't have a chance to discuss this, but I want to show you that we have action maps in JZ, JR, and J5. That's the same as LZ, angular momentum around the center of the galaxy. So we have action maps as a function of metallicity for the alpha-rich and the alpha-poor component. And it's these things that we've been trying to match to cosmological simulations, working with people like Andrew Wetzel. And I think Phil is involved in that work as well. And what you see is that these action maps with metallicity are really quite curious. And the alpha-rich component in JZ and JR, it was unexpected. And we still don't have a good match. But it's something to do with the alpha-rich component having been formed as a small, very sort of turbulent, violent disk at high redshift. How it settled and how it settled down and interacted with the rest of the galaxy is a very interesting problem. But anyway, it just shows you what you can do when you start combining actions with chemistry. But what I want to do is to get onto the phase spiral and talk about that and give a reason for why I think the phase spiral exists at all. But before I do that, let me just quickly show you that the Gaia survey again allows you to slice this action slice this phase spiral in different ways. I can do it in actions. That's JR. Basically, that's large radial action, small radial action. Small radial action would be circularized orbits. So you're seeing a very clear phase spiral coming from the younger stars on the circularized orbits. Anyway, you can do this in action space. You can do this in location. You can move your volume around. You can go in azimuth. You can go in or out of disk. And again, you find that this phase spiral evolves its character for reasons that we think we understand. That's not, again, pertinent to the models I'm about to show you. Something else is chemistry. You can distinguish whether the spiral is seen only in the alpha-poor disk or is it seen weakly in the alpha-rich disk. And there's weak evidence for it in the alpha-rich disk that you see here. So basically, it's a disk-wide phenomenon that both the old and the young stars and the metal-rich and metal-poor stars are all affected. But the strongest effect by far is in the circularized stars close to the plane. And you can also do it by age. The Gaia photometry is very, very precise, but it gives you a crude model for age. And you can separate out the disk in terms of young stars and older stars, and you find that the phase spiral is more prominent in the younger stars which are highly circularized towards the plane. So this is all going to be redone with the new DR3 release. In fact, you can do it ahead of me since it's been released now. Anyway, one more thing to say is that the phase spiral is particularly prominent when you code it in terms of angular momentum. That's the J5 or LZ. This is what involves Julia Kana. And he was able to show that it's a particularly clean, you get rid of a lot of the substructure that you see in the other dimensions if you go to angular momentum space. So there's something about preservation of angular momentum which is important for understanding this phase spiral phenomenon. All right, so let me get to the main thesis of my talk, which is basically, I keep this quite concise and get to the punchline fairly easily. So there's lots of ideas being proposed now about where the phase spiral has come from. People have talked about star clusters expanding, giving you some kind of coherent effect as the stars start to oscillate, because it gives you a sort of release of stars with certain actions. People have talked about the bar buckling effect at the galactic center. There have been a number of ideas out there. But I think the one that has attracted the most attention by far is the idea that something has punched through the galaxy now or in the distant past, and has created this rather bizarre phase spiral phenomenon. So there's a question for you right there. You know, you see a phase spiral, is it long-lived? If it's short-lived, let's say it's 100 million years old, then it would have been something that's passed through recently. Well, there's nothing passing through in the last 100 million years because Sag is coming back now. But if you find it to be long-lived, like 1 or 2 or 3 giga-years old, then maybe it was a previous passage by a very massive object that triggered this. So this is the whole point why people are very excited by it. And it also talks to the issues of, do you see the impact of the momentum conservation, energy conservation, or is it to do with dark matter halos being different beast altogether, like these weird bosonic halos? So there's all sorts of other implications for what you think dark matter is as well. So I'm not concerned with that. I'm much more concerned with classical dynamics for this particular work. So Schoenrich and Binney in their paper, Binney and Schoenrich talked about this being an impulse from a mass of about 10 to the 2, 10 to the 10, which is the mass that most people have fixed on. That has a problem because what you see in stars today is below 10 to the 9 in Sag. I think it's like 3, 10 to the 8 if you believe Vasiliev and Wynne Evans' latest paper. But what Binney and Schoenrich say is that you need something like 100 million particles in an n-body simulation to do this properly. Theirs was a theoretical model. And basically what you need to do is create an impulse. So having an n-body mass, like say an LMC, SMC type mass or Sag mass go through is not very helpful because you want this thing to disappear to look at the truly impulsive effect. But also you want to look at the effect of a dwarf going through multiple times, as you see with most models of Sag. So you want to look at both of those. But we went with the impulse model because we went with the Sag model in the previous paper, and it ends up being a very, very complex mess. And it raises too many issues. So we went back to looking at a simple impulse so we could compare with the Binney and Schoenrich theoretical model. And that ended up being a very useful thing to do. And by the way, what we've learned to use is A gamma. We feel now that all modelers of the galaxy or M31 need to do this. A gamma sets you up so that the initial conditions that you define in terms of distribution functions, the galaxy settles very quickly and has long-term stability. You don't evolve for something else, which is not what you specify, which is the way that a lot of this work has been done for decades. So we work with Ramses because Roman Tessio was very kind to us and allowed us to insert a true impulse, a mass that goes through and then eventually fades away exponentially. So we could simulate the effect of a true impulse, which we were doing with sync particles. And at the same time, he was allowing, we were using a gamma to set up the model so that we knew that when the model was evolved, when the model was triggered, that it wouldn't evolve. You wouldn't get redistribution of the bulge, disk, and halo over the course of time. So these were very important, I think, to get to see what we see in this current work. So let me show you quick 2 simulations. The first one is to show you that over billions of years, and this uses the parameters from my paper with Gerhardt on the galactic parameters. So it's got the right bulge, the right disk, and so forth. And you're watching that evolve sped up over 1 billion years. So if you evolve it over 4 billion years, this disk doesn't evolve at all. It's got the vertical heating, there's no vertical heating. I'll show you the results in a moment. So when we get to hit that with a perturber, this is a transient perturber. A perturber crosses through the disk and then fades away. So you don't get any impulse when it comes back through. All right, so let me show you what this looks like. So now there's the mass passing through, and it generates this density wave phenomenon, which is wrapping up with the differential shear of the disk. It also generates bending waves, and these bending waves also wrap up with the differential shear of the disk. And these, I feel, are the important insight that gets you to understand what's going on with the phase spiral. I'll run that one more time. So there's the mass going through. That mass then fades away, and you generate this rather clean structure. The disk is very cold. As I said, it's very long-lived. So let me show you, first of all, that the disk really is long-lived. So here are the various components. This is the rotation curve, tangential rotation curve, dark halo, disk, and bulge. And the solid line is T of 0, and the dashed line is T of 4 gigayears. Surface density as well doesn't show any evolution. Now look at this is the real killer. This is the real telling insight. Look at the vertical dispersion, Z with time. And you'll find that most people that simulate disks, I think it's even true of the cosmological disks, and it's probably because you have less than 100 million particles, and which is what we found that 10 million particles wasn't enough to get this right. But you notice that the vertical dispersion profile at 0 and 4 gigayears is identical. The one thing we do see, which I don't quite understand, is that the radial dispersion profile shows a very weak evolution over 4 4 billion years. And someone like Phil, who works on this kind of thing, might understand that. But for now, I don't quite understand why that Greek evolution is present. So here's the first thing that we find, and I'll show you the phase spiral predictions in a moment and what we learned from this. The first thing we find is that you can fit a simple Lindblad-like model. The actual equations are given here. This is the azimuthal angle as a function of radius and time. And that omega is computed from the local disk. That's just V phi over R. That's the local radial frequency. And that comes from the effective local effective potential. And you can compute all of these things. And you find that the disk wraps up as it's shearing. So that basically the density wave is wrapping up because of the shear and not much else. The pattern speed is tiny. Initially, it doesn't. You see that it doesn't quite match the predicted shape at 190 megayears. But as you go forward in time, you do get to that functional form. So I fitted it in the future and then demonstrate what it looked like in the past, basically. So basically, we have a very simple model that tracks the density wave over 1 gigayear, it says here, but in fact, we've traced this now to 1.9 gigayears in our latest round of simulations. But something else that you find in these simulations, which is really interesting, is that there's a bending mode. Now, here's my simple model to show you what I mean by a bending mode wrapping up. This is a sort of a cos2 theta function. White means that this is moving towards you or it's displaced towards you. Black means it's displaced away from you. And if you put a differential shear in there, you see it wrap up from the inside in this rather interesting way. And don't forget, you have the same pattern of frequencies, like Lindblad resonances, vertical to the disk as you do in the plane of the disk. So the vertical oscillation also has a coupling behavior with the angular frequency. So when I look at that, this is the form that's given in Binion Tremaine, which is the form that we fit. And the vertical oscillation frequency is also dependent on the effective potential, but with respect to Z this time, not with respect to R. So what's really interesting here is that this frequency is not the same frequency as kappa. This frequency is always less. So what's happening here is that the bending mode is wrapping up at a slower rate than the density wave wrapping up. And I think that's what we're seeing in terms of the phase spiral in the Gaia data. So let me show you what this looks like. So this is at T of 0, T of 95, 143, 190. Green is moving, is displaced towards you, pink is displaced away from you, purple is moving towards you, it's velocity now, plus 5 kilometers per second, and orange is moving away from you. And by the way, you can see these effects in external galaxies, we're quite sure of that. So as the perturber goes through at T of 95, there's the perturber right there, going through, the transient perturber. And the first thing you notice is that stars move towards the perturber, which is pretty much what Binion Tremaine find in their, Binion Schoenrich show in their model. And that's what sets up this m=1 mode initially. And this then transforms to an m=2 mode in the inner disk, which then takes over the overall disk itself. So you can see now how this is evolving with time. This is in displacement, and this is in Z, delta Z, this is delta VZ. So if I go forward in time, these circles are where I extract my phase spirals from in a moment, so just ignore the circles. But notice now that there's a bending wave that wraps up in displacement and velocity. You see that now moving forward in time, 285, 380, 476, 571, and so on. So this thing is basically wrapping up as you go. And these circles, by the way, 1 is the solar neighborhood. 2, 3, 4, 5, 6. The antipode is over here at 7. And these circles are circular volumes where we've extracted our phase spiral predictions. So you can keep on going into the future. This is 600, 700, 800, 900 million years. And again, you see this behavior. And a very keen eye shows you that the spiral density wave is wrapping up faster than the bending mode that you see in pink and green and purple and orange. All right, so now I overlay these results. So I've overlaid the density wave as spiral arms. You're seeing the arm and the counter arm. And on top of that, I've given you a simplified view, a smooth model version of the previous results. And you can see now that the bending mode wraps up as you go forward in time. This is the fit to the data. But the density wave is wrapping up faster. It may not be so clear to see. So what's happening here is the density wave, where you basically compress stars, is riding the bending wave. rather like a sort of a roller coaster or something, or seeing a piece of string and watching the surf rolling in on Australian beach. Basically, what you're seeing is a dense filament which is rolling over these bending modes. I think this is exactly what is causing the phase spiral effect, which has important implications. All right, so going back to Heidi Newberg, when they were looking at these local wave-like phenomena, they were the ones that found it in the local disk. They didn't have a holistic appreciation of what it was doing on the galactic scale, but they had a local appreciation of what they were seeing. They produce these rather nice cartoons. They've drawn them here as being like ripples on a pond, and they've superimposed that here on the Milky Way. So there's some kind of interaction between ripples and density arms. But this is not quite the picture as I see it, not from the simulations, but it's what we've been calling the roller coaster model, because it seems to be difficult to call it anything else at the moment. Anyway, so now what I want to show you is how all this ties together and what we learn in terms of galactic seismology about the perturbation, and what we hope to learn very soon. So what we're trying to reproduce is this ZVZ diagram encoded in V-Phi. And what I've done now is to take, this is the solar neighborhood, this is the antipode region over here, 2, 3, 4, 5, 6. And basically what I've computed is the phase spiral in the V-Phi and VR encoded space in each of these volumes. So some of these look rather good, and they sort of spiral into the center rather well, and you see that in both VR and V-Phi. So whatever action you have vertically is directly affecting the radial action as well, which is what you always see in these sorts of impulsive simulations where you have bending modes working with these density waves, which is really interesting. But what is particularly interesting is I do not see any relationship between these phase spiral diagrams and what I see moving in or out of these projected volumes. So what you're seeing here, as Feynman would put it, is a summation over history. So whatever happened in that volume has happened over a very large span of time, and it builds up something coherently if enough time has passed. So what I want to do now is show you something important about what I think is the trigger of all this and how it works with the local disk and where the impact passed through the disk. So these volumes from 1 to 12, so 1 is, as I say, the solar volume. I've now reduced a bar chart, a wall chart of all these phase spirals. So for the moment, ignore the boxes. These rectangles and various box regions are discussed in the 2020 paper. But the first thing to notice, so this is at T of 0. Volume 1 is here. Volume 2, 3, 4, 5, 6, and it goes back to 7, 8, 9, 10, 11, 12. So initially, there's nothing happening because the impactor hasn't yet arrived near the disk. This is 48 million years, 95, and so forth, all the way up to a gigayear, pretty much a gigayear. And as I say, we've evolved this to 2 gigayears now, and we find that this phenomenon is easily visible out to about 1.5 gigayears and starts to fade. So it does seem to last a very long time. And you can see how this phase spiral phenomenon, it starts in one region of the disk. Basically, it hasn't spread around the azimuth, but as time passes, it does spread around the complete azimuth. And this is in V-Phi, and this is in VR. Now, what's really interesting, if you look carefully, if you blur your eyes, is there's a banded structure across these diagrams. And that banded structure is really intriguing to actually understand where that's come from. So basically, look at this diagram, look at these black boxes. What's going on here is when the impactor crossed over here, this is this row here, the third row down, the impactor, all the models have the impactor crossing along the sun's radius vector, but not at 8 kiloparsecs, more like 18 kiloparsecs. So because it's a differentially rotating disk, the solar neighborhood does a full orbit, and meanwhile, this has only moved halfway around the disk at 18 kiloparsecs. So the solar neighborhood doesn't catch up with the impactor region for 400 million years. So basically what's going on here is you're seeing where, when the impactor site lines up with the solar neighborhood. And basically these boxes are showing you that essentially that banded structure is a direct consequence of the solar neighborhood coming back round and meeting up with the impactor radius vector every 400 million years. So basically the outer disk, the flapping of the outer disk is preserved, at least in these simulations, for a very long time. You see that the reverberation in the outer disk for at least 1.5 gigayears. And we feel that this is what's actually driving the phase spiral structure. So let me finish up. I think I have 5 more minutes. So basically, here are the issues that we want to address. What caused the phase spiral, how long ago, where and how fragile is it? How robust is this a mechanism, or does it, for example, does another crossing through the disk essentially wipe out the phase spiral? And there's also the issue of the specific mechanism that you're seeing. How do you get the entire disk in this coherent way to oscillate? So the weakness of the entire work to date is that the mass that we're all using is 2 10 to the 10 to the 10. Yet the Sagittarius dwarf that we see approaching the disk now, from work from the photometric surveys and the apogee survey, says that that perturber mass in stars is something like 2 or 3 times 10 to the 8. And so you'd say that the halo, dark halo mass, let's say, is only a factor of 10 bigger than that. So we seem to be a factor of 100 larger than the stellar mass, and a factor of 10 larger than what you might imagine dark halo mass is, especially because it's being stretched as it falls in, and that weakens the impulse as well. So I've put in those masses through the disk, it does essentially nothing. So basically, you need to be at a minimum of 10 to the 10 to really get this phenomenon going. So the only way I see to resolve the issue is to say that, in fact, what we're seeing today is not the trigger. What we see today, in fact, every model of Sagittarius moving through the galaxy basically has it on this trefoil orbit. It's been through at least 3 times. Some people say as many as 5 or 7 times. So it was much more massive in the past and has been stripped over the course of successive transits. So I would argue, I don't know if this is correct at the present time, but I would argue that the impulse that we need is not what we see today, but what happened in the previous crossing. And the previous crossings were 800 million years ago, possibly 1.5 billion years ago, and so forth. So I think that I would argue that the impulse probably is correct, but it's preserved from a previous crossing when Sag was much more massive. So anyway, this is my last slide, looking forward. So what we've been doing now, we've chosen the Q value that keeps the disk very cold and smooth and doesn't trigger bars and spiral arms for a very real reason. That we want to understand the reaction of the disk to the impulse. But in fact, we're already running simulations where we allow a bar to form, we allow spiral arms to form. And we haven't yet done them, but we're trying to run simulations with the same technique where we bring in the sort of 8,000 giant molecular clouds, because they're also known from Dongyu and Hernquist's work and other people's work to trigger sort of buildup of spiral amplification, and that also generates local density wave structures. So essentially, we need to make the disk more sophisticated and see if the presence of a bar, if the presence of the spiral arms and molecular clouds tends to reduce the contrast, or even help rather than hinder us. So where we are right now is getting to more sophisticated simulations. We await, of course, Gaia DR3. And we also need to bring all this to bear with the new the Gaia survey DR3 release. Anyway, I'll leave that with you, and we'll take questions. Thank you.
Okay. Thank you, Joss. That was very interesting. So I believe the way we're asking questions is to have people raise their hand. And is that true, Mansi?
Yes, or I mean, if you can't find your raise hand feature, just type your name in the chat window and we'll keep an eye on that as well.
Okay. So you have a question from Carl Wilma.
Hi, Josh. That was really interesting. I'm still a little unclear on the lifetime of this phase spiral, and could it be that it's not Sagittarius, but could we trace it all the way back to Gaia Enceladus or something?
That's a very interesting question. I've seen orbits for Gaia Enceladus from the Cambridge group. I think Dennis Urquhart was the one that was doing this. I think he's at Surrey. I believe the total mass of that system was of order what we see now in Sag. It wasn't a massive enough event. I don't know how complete their sampling and selection is, whether they have a complete model, but it's also a radial plunging orbit that gives you some kind of a box structure. So it's crossing a lot of times. I think the outer disk impulsive action is a cleaner way to do this. So it was Sag, I would say, more massive Sag, or it was something else that we haven't yet identified on the other side of the galaxy or something. But a good point. People have raised that issue with me. I do think you have to get to 10 to the 10. I think we've tried simulations with 10 to the 9. We've even published in 2019. It gives you nothing at all. And others found the same thing, that you, like Shervin Laporte does some very nice work on this and finds you need 10 to the 10 at least, or more. In fact, some of the models I've seen say it should be 10 to the 11, which is embarrassing.
Wow.
Okay, I have a question, or two-part question.
Who's speaking, by the way?
This is Chris.
Oh, Chris, sorry. Apologies.
I don't know whether my video is showing up or no, I guess not.
Oh, but I only see 5 names at a time on my screen. I don't see the full.
Yes, sorry. So the first question is, to what extent does this result or similar kinds of results constrain either the structure or nature of dark matter? And you mentioned that as a possible, something, an ingredient of a future model. And the second question is there any hope of seeing these kinds of phenomena in external galaxies with integral field spectroscopy, for example?
Yeah, so the nature of dark matter question is something which others have talked about doing. The one thing we don't have at the moment, we have a smooth dark matter halo, not a live dark matter halo. In fact, Sheckers and Widrow paper I referred to earlier did a very nice analysis of the Fourier modes that kick in when you have these live clumpy halos. So that's something else we haven't done. And it sort of generates a sort of a background pattern. I don't know if it has a collective effect yet, but it certainly generates noise and makes things much less contrasty. But that's not something we haven't done. But on the exciting idea of sort of the who's this guy, Mose at Harvard and Richard Easter in New Zealand, they've presented dynamical models of these sorts of bosonic wave function dark matter halos. I believe these don't give you dynamical friction. They don't give you energy or momentum. They don't absorb momentum. So I can imagine all sorts of ways that things don't reproduce if you're using those sorts of halos. So I don't know the answer, to be honest with you. I've stuck with the basic classical stuff because this is already a lot of hard work getting this work done as it stands now. But I am absolutely sure of the fact that if people were able to implement this, I think Phil Hopkins may have worked with, is it Philip Mose? Is that right, Phil?
Yes.
Yeah, you would be the right people to show us how you, because we're getting to the point now where there are so many high order effects that we're seeing in the Gaia data, in addition to the models, that surely it's just a matter of time. For example, even if you don't do momentum conservation, for example, if you just have a static halo and drop this stuff in, you get a different bunch of patterns, which looks nothing like the Gaia data. So even that simple fact of conserving momentum has an impact on the results. Notice also we haven't brought in here any age information in the modeling, any chemistry, any of the other fine stuff that we observe. So that is also something which needs to be brought into these models, because that must give you more lever arms as well. So I can't answer your question quickly. In terms of looking at these wrapping up bending modes in external galaxies, yes, they have been seen. There are at least a dozen galaxies in ionized gas, mostly in H1, I think, where you see what looks like the m=1 warp propagating inwards into some kind of wrapping up bending mode. So these are galaxies within a sort of 50 megaparsecs. So yes, the velocity resolution you'd need, though, is of order 5 kilometers per second, let's say, 10 kilometers per second. So I think Muse wouldn't quite be good enough, but maybe something on the CAC might get you there.
KCWI gets to R of 20,000. So.
Yeah, and I think you're better off looking for this in starlight. I think the gas certainly does behave in the same way.
Yeah.
In fact, the young stars seem to indicate that this phase spiral is very evident. So presumably the young stars are being born, and A and B stars, OA and B stars are being born in this gas. So they've come from the mother cloud in recent history. So they presumably are reflecting what the gas is doing as well. So I presume the gas also shows the exact same imprint, although no one's yet done the simulation like this with gas in it. But two very interesting questions to go after. I
Okay.
see hands going up. I think Carl had his hand up with a.
Carl put his hand down.
All right.
Anyone else? Okay, well, let us, I don't know how we thank our speaker. I will give you a little
The sound of one hand clapping.
And I would like to say that if anyone wants to, yes, if anyone wants to speak with Josh who hasn't signed up yet, just email me and I'll put you on the schedule. Of course, his time zone is a little bit different than ours, but astronomers work late, so shouldn't be a problem. And I guess we'll adjourn this.